Saucier, this is a lesson on connecting the concepts of instantaneous rate of change and area under the curve. I'm going to start with a simple position graph. I'm going to graph position on the vertical axis as a function of time. And I'm going to think of the context of driving a car while I do so. So if I say measure time in hours and go for 1 hour and change my distance from my initial starting point to be 60, then I could imagine driving a car at a constant velocity, changing my position so that after 1 hour I've gone 60 miles. And if I go for another hour at the same velocity, then after 2 hours, I will have gone 120 miles. This is a simple position graph. And I know that the rate of change of position is the concept of velocity. We can use position information to get information about velocity. And if I had a position graph, I could make a velocity graph from it. I'm going to do that. I'm going to have the same horizontal axis labeled time with the same intervals. This is a velocity graph. How do I use the position to get velocity? We've been working with the concept of instantaneous rate of change. It's the slope of tangent lines on a graph. The slope of this line is going to be the same at any point along the line. Because this position graph is a line, the slope is constant. Constantly what, though? Well, if I start at 0 and go over 1, I have to go up 60. So the slope between those two is 60. And the slope at any point is the same 60. So on my velocity graph, I have a constant slope of 60, which makes a constant function of 60. I could write functions for the position. Position as a function of time, given this information, is 60 times t. This is the equation of a line, a simple line with a slope of 60. And the velocity as a function of time is a constant function, 60. So starting with position, the instantaneous rate of change will give us velocity. But what about going in the inverse direction? What if I start with velocity and I'm interested in understanding or getting information about position? How do we go in the opposite direction? Well, let's analyze this simple situation. If I was given the velocity information, the velocity graph, this constant 60, look at the area under the curve of this velocity graph. Its shape is a rectangle, so its area is simple to calculate. We've got a base measure of 2 and a height of 60. 2 times 60 is 120. So after 2 hours, the area under the velocity curve is 120, which corresponds to the position after 2 hours. Let's do this again. After 1 hour, the area under the curve of the velocity function from my starting time to 1 is a rectangle, so it's easy to calculate. That rectangle has a base of 1 and a height of 60, making the area equal to 60, which corresponds to the position after 1 hour. In other words, in general, the area under the curve of a velocity function is position. we have calculus terms for instantaneous rate of change and area under the curve. IROC in calculus is better known as the derivative. And area under the curve in calculus is better known as the integral. The integral and the derivative in calculus are inverses of each other. You can go from one and back. Some might wonder, well, if we have velocity information, what happens if we take the derivative of that? Well, when we do, and we can, we get the concept of acceleration. The instantaneous rate of change of velocity is the concept of acceleration. And if we had information about acceleration, we could get information about velocity by taking the area under the curve, the integral. This can be done conceptually, it can be done with the graphs, and it can be done with equations. And in a nutshell, that's what we do in calculus.